Mm. Okay, welcome everyone to the week 3 live session of this course on integrated waste management for a smart city. So I will first briefly introduce myself. I am the TA assigned to this course and currently I am a research scholar under the PMRF scheme and I'm working under the supervision of Professor Brajesh Kumar Dubey and Professor Makarand Madhav Hangrekar in the Department of Civil Engineering in IIT Kharagpur. So as a part of our deliverables, as per the PMRF scheme, we are supposed to do TA-ship under various platforms, and NPTEL is one of such platforms that I have chosen to uh, perform this duty for myself. And as a part of this live session, what we are doing for the past 2 weeks as well, that on every Monday we meet from 7 to 9 p.m. IST, and we go through a set of 15 questions. We discuss them. Along with it, I would also prefer to have a very interactive session in here. Like if you have any thoughts, any points that you would like to discuss, you are very much welcome to share it with us so that it is kind of a knowledge sharing session. And I can also try to pitch in some points from my end that I might find relevant to this particular course. So I can see that it is already 7 and I will start sharing the questions with you. And in today's questions, it is a kind of a numerical questions are also there, which some of which are a bit, you can have some time for yourself, like they are a bit long. So you might take 5 to 10 minutes to solve them. And otherwise, we have also some normal theoretical based questions as well. So now continuing the session. So starting with the first question. So the first question is, I will give you 4 options, and among them, you have to state like which of them is the composition of a waste that is considered for characterization in order to judge its combustion potential. So I will just type it here as well. So the question is, which of the following combination of the waste composition can be considered for characterizing the combustion potential of a solid waste? So this combustion potential is the main target in here. So I will just put it in bold. And your options are fixed carbon. Okay, so these are the 4 options. Which one do you think is the correct answer? You can unmute yourselves and share your opinion, or you can also use the chat box for the same. Okay, I can see that most of you have selected option A, that is fixed carbon plus volatile solids plus inorganic plus ash and water. Yes, that is absolutely the correct answer. So this is how we characterize the combustion properties of a solid waste. So moving on to the next question. In here, we have a chemical known as EDTA, and you have to calculate its heating value. So I will just type the name EDTA. Its chemical formula is C10H16N2O8. So this is it, and you have to calculate its heating value. and the unit it should be is BTU, British thermal units per pound. And your options are, all of the options are in BTU per pound only. So I will just type the values. So these are the values. Hint, if you require, I can give you. You can use the chat box for the same. Okay, so the hint for this can be like you must have, while in the classes, you must have heard about the Dulong's formula that uses, which is basically an empirical formula that uses the carbon, hydrogen, oxygen, sulfur, and nitrogen content in terms of percentages is included in that formula. So that is used. I will also, since it is a bit difficult to memorize the formula, I will also write it here. So the BTU is, and this is oxygen by 8, not H by 8 also. This is just O is oxygen by 8. Yeah. So this is called Dulong's equation. The C, H, O, S, and N, these are all in percentages. Like what percentage of C is there in this chemical formula, what percentage of H, like that. We can have another about 7 minutes on this question. Okay, so we have one answer from Manu. It is 6070. I will wait for some more time for others to attempt it, then we can solve this question. Anyone else have got any answer? Fine, so I think we can discuss it now. So just as I said that in this formula, everything, the C, H, N, S, and O, everything will be in percentages. So first things first, I need to determine what is the percentage amount of C and other elements. So starting with C. So what is the formula? It is C10. So there are 10 atoms of C, each weighs around 12. Molar weight is 12 grams. So going by that, and then divided by the total weight, that is 10 into 12 for C itself, followed by we have 16 into 1. 1 is the weight of hydrogen atom into 16, that is the number of atoms, or I can just write it like this: 16 into 1 plus how many nitrogen, 2 nitrogen atoms we have, each weighs 14, so 14 into 2 plus, okay, 8 oxygen we have. So this is the total, and in order to determine the percentage, I will multiply it by 100. I will just use calculator to quickly calculate it. So the denominator seems to be 292 and the numerator is 120 into 100 divided by 292. So the carbon percentage is around 41.1%. Similarly, I will calculate the same for H, percentage H. So the numerator will be same, molecular weight, and I will just substitute the total weight of hydrogen present in that atom. So 16 atoms of hydrogen, that means 16 into 100 divided by 292, which is around 5.5. Similarly, oxygen, 43.8, and nitrogen will be around 9.6%. So putting all these values in the formula, the DeLong's equation, I will have BTU by, no, sorry, not by, per pound will be 145 into percentage of carbon, 41.1 plus 610 into 5.5 minus 43.8 divided by 8 plus 10 into 9.6. So the sulfur, since my equation or my chemical formula, it doesn't have any sulfur, so S will be 0. So that is why 40 is 0. So we have ignored it. And if I try to calculate what this sums up to, it will be yes, the answer is coming somewhat 6070.75. Yes, so the closest one that we have in our options, it is 6070. So that is why it is the correct answer. And in the meanwhile, I will also try to explain you like what is the physical or practical significance of these two particular questions. So for example, the previous one where the combustion characteristic of a solid waste was being determined. So in that, why do we require to do this characterization? For example, if I have any solid waste, municipal solid waste, it is a heterogeneous mix of variety of compounds, a variety of materials, compounds. So I am looking at it from the perspective of combustion. So when I am combusting it, the primary materials that I need to add it to its calorific value. Yeah, so the primary materials or the primary fractions or components that I need to enhance its calorific value, it is basically fixed carbon. While the volatile solids are also important because it is which defines what is the ignition temperature will be, how quickly it will catch fire and stuff like that. So fixed carbons and volatile solids, these two are the ones that aids combustion. On the other hand, water, as we all know, in the last live session also we discussed that water, the more the water, the more is the latent heat of vaporization of water. So if my solid waste obviously is having more water, the amount of energy we can derive by burning it, it will be like obviously less. So that is why that is another factor. And in inorganic component, what lies is that inorganics may have, like when I have a very mix of a heterogeneous mix of a solid waste, it can have inorganics in the form of like dust, sand, all those stuff can be there, along with glasses, some metals. So these inorganic materials are included in this bracket. And ash, like when we say ash, what is ash? Ash is something that is left behind after the combustion is done. So if I am seeing like I am burning 1 kg of two materials, like each material is 1 kg each, and I am burning them, and after the entire combustion process is done, in one part, let's say 200 in 1 kg, 200 grams of ash is generated, and in another one, 500 grams of ash is generated. So the higher the ash content, the lower will be its calorific value, because if a material is having and it is some fraction of it is ash, and ash doesn't really contribute to its calorific value or the heating value of a material. So the higher the ash content, that means it is a useless part from combustion perspective. That it is a useless part, and it will bring down my heating value of that solid waste or any other material. So that is why whenever I am trying to use something, some solid waste or any other solid material in terms of a as a fuel, solid fuel, then what I want is that my fixed carbon content should be high. My volatile solids should also be somewhere in an optimal range, but all should be definitely be lower. It is like inorganics should be less, ash should be less, water should be less. So that is how, like, I have given you like 4 or 5 types of material, and I am asking your opinion, like which one do you think we should use for combustion in any coal-fired power plants? Like coal, we know it is a fossil fuel. We import it from Australia and then burn in our power plants. So what we like people do is that they substitute some amount of the coal with other fuels, which can be some of the renewable part can be the solid waste, or there is other refuse derived fuel also. So whenever you are an engineer and I'm giving you 4 or 5 streams of fuel, so you will take a look at its each individual type of solid waste or any fuel material. You will look at its combustion characteristics, and you can see like whichever fuel is having high inorganic ash and water, you will clearly exclude it from the prospective fuels or put it at the lowest priority. So that is how it really plays a very important role. Now, this was the practical significance of the first question. Now, coming to the second one. Okay, yes. So this is the second one where you have to calculate the heating value. So first things first, EDTA is a chemical. So for that, so we can have this chemical formula. But in the last class, we were also discussing about ultimate analysis, where we get a fuel, we determine its C, H, N, S, and O. These 5 elements, sorry, 6 elements, we determine the percentages of those or fraction of those in a material, and then based on that fraction we can also formulate such formulas, these kind of formula. So it can be a simple chemical like glucose or something like that, or otherwise we can also assign a formula to a very heterogeneous mix of fuel based on its based on its ultimate analysis. Now once we have this formula, we can use it to derive its heating value, also known as calorific value, and that is very frequently calculated with the help of Dulong's equation. So this Dulong's equation, it is an empirical formula derived from various statistical analysis and particularly aimed at the solid waste management, and it's used for energy for this combustion characteristics like that. So this is how we use the first we do the ultimate analysis, get this percentage of carbon, hydrogen, nitrogen, oxygen, sulfur, put it in this Dulong's equation, and then we calculate like what is the heating value. So if a material is having a certain optimal or more than that heating value, which is suitable for its use for combustion, for generating maybe electricity or heat, then we choose that fuel, we go ahead with it. That is like, this is one of the perspectives that we look at. Then another one can be, there are very other methods, like this is how we determine the heating value, like numerically or based on a formula. But what should be the ideal way to do that? It is through an instrument which is known as bomb calorimeter. In bomb calorimeter, we put in some mass of material into an instrument, then we burn that instrument in the presence of oxygen. So the amount of heat that is generated, it creates a temperature difference, and based on it, the computer is there, it calculates the heating value. So this bomb calorimeter, it gives me the actual heating value that my solid waste or any material that I want to try, it is exhibiting. But for instance, this bomb calorimeter is an expensive equipment and not all labs have it. So in its absence, what we can do is that we can use the Dulong's formula to calculate its heating value. The accuracy, of course, it can vary significantly, like a material, for example, which is showing 6070 in Dulong's equation. It can very much be possible that in when we run it in bomb calorimeter, it can be very much as 5900 or 5000 in fact. So this can vary because it is a Dulong's equation is a very generalized form of equation. And if you try to look into the literature, like you will find that people and researchers, what they have done is that they have derived similar equations for calculating the heating value for different types of equipment. In fact, like what you can do is that for your, if someone is residing in Delhi, someone is residing in Kolkata, like due to the living standards or lifestyle of the people are very significantly in these two places. So that is why researchers can also work on those specific geography or location specific solid waste, and generate such similar to Dulong's equation some location specific calorific value equations as well. And in fact, various countries and many researchers have done this also. So this is one way where you can derive such formulas based on the location where certain quality of waste material is generated. Apart from that, for example, you are having uh, like a very specific waste stream. For example, in agricultural sector, after harvesting, like you get a huge amount of agricultural residues left, which we often hear that stubble burning and all, it is causing problems in Delhi, Haryana, and all those places. So that thing can also be again used as a fuel. But if you apply Dulong's formula to for the combustion characteristic of those stubbles or agricultural residues, you will get some value. But like I am very much sure that that value is not the exact one that the stubble or the agricultural residue actually exhibits. So that is why people also study individual type of materials. For example, it can be agricultural residues. For example, people who are trying to use sugarcane bagasse. Like sugarcane, it is used to generate, we all know, sugar and ethanol. After generating that, sugarcane bagasse is left over. So that material is often used for like that material is often combusted, and the generated heat is used for either electricity production or simply in the internal processes as a heat source. So there also you can analyze, get the ultimate analysis done, uh, go through the statistical processes to derive similar equations that are more specific to a suitable or a particular type of feedstock or the material that I'm trying to burn. So this is the practical significance of these two questions. So now we will move on to the next question. Okay, so the next question is a very simple one. I hope you can answer it within 30 seconds. I will give you four options and you have to say which is the preferred measurement unit for chemicals present in solutions. Very simple. Solution. And your options are, pardon me, this milligram M should be always small letters, and due to the typo, it is becoming capital, so kindly ignore it. Okay, so among these, which is the correct answer? Very simple question. You can have 30 seconds. Yep, option B is the correct answer. So then the next question. Now this is a simple, very simple question. Here you have been provided like the chemical analysis report of a wastewater sample, which provides the biochemical oxygen demand content of the wastewater and its value is given in percentage, BOD value, which is 0.05%. So what is the equivalent concentration of BOD in milligram per liter? So I will give you the, so BOD is given in 0.05%, and you have to determine its value in milligram per liter. This is the question, and your options are, these are the options. Okay, 500, that is the correct answer. 500 milligrams per liter. So how did we get this answer? It is very simple. So 1% in solutions. 1% basically means 10,000 ppm, parts per million. So, and parts per million is equal to milligram per liter. 1 ppm is equal to 1 milligram per liter. So, just using the same thing in 0.05%, we will get 500 milligram per liter as the answer. So, the next question is a true and false type. I will first quickly write the sentence in here. Okay, so this is a true and false answer. What do you think about it? Any thoughts on this? Okay, false. Dry and wet waste should be segregated. Yes, that is correct. But can something else be also added to that? Yeah, bio, non-bio, and hazardous. That is the correct answer. Because like in our households also, in the form of hazardous waste, what we generate, there can be like small batteries that we use that is coming under the hazardous waste. Similarly, any other stuff that such contains such chemicals can also be present from our households. So as per the 2016 solid waste management guidelines, we should segregate organic fractions in one place, inorganics in another place, and hazardous waste in another place. Or so for example, if I am having some sanitary wastes, napkins like that, so that should be wrapped and packed inside, like various brands, they provide their own packaging materials, so that should be carefully wrapped in it, packed in it, put inside it, and then should be thrown either in the hazardous or in the dry waste component, or the non-biological component there. So that is one part in this. Now coming on to the next question, which is also a small and simple one. And your options will be, okay, so which one do you think is the correct answer? like 4 calibration curves have been generated, and based on its R square, which calibration curve do you think is acceptable? Okay, so first I will briefly share with you like why we or certain examples where we use the calibration curve. For example, I have a material, a liquid sample, and in that liquid sample, I have dissolved some amount of glucose. And now I have to use spectrophotometric UV spectrophotometer to determine the concentration of glucose. So what UV spectrophotometer does is that it is a analytical technique where you throw or put a stream of UV light through your sample, and when it passes through its sample, there is certain absorbance of that UV radiation. So based on that absorbance, we try to determine the concentration. So if I am trying to determine the glucose concentration of an unknown sample, first what I will do is that I will prepare some known samples. For example, I will one sample will be there which is blank. In there, it will be completely plain deionized or distilled water. In another sample, let's say it is 10 milligram per liter concentration of glucose we have prepared. After that, 10, 20, 40, 80, like that, like 5, 6 points we have prepared. So these all concentrations are known to us, and we put this known concentration samples in that instrument spectrophotometer, and then we see like for those known concentrations what is the absorbance value that the instrument is telling us. And so based on that absorbance value, I will also plot a graph so that will be easier to understand. Okay, so let's say this is known concentration in milligram per liter, and this is the absorbance. So let's say these are the absorbances, and we do that at a certain wavelength. And first absorbance is 0.006. Then I get, so these are the, let's say, absorbances that we got. These were the known samples, and we got these results from the instrument. So I will plot a graph. Okay, due to some reason, I'm not able to plot this. Let me try something else. Okay, let me just try some normally. Okay, so this is my y-axis, this is my x-axis. X-axis is the known axis for which we have the x-axis will be the concentration or concentration, and y-axis will be the absorbance. So when we plot the calibration curve, so that based on the known concentrations, like 0 will be somewhere here. So for it, we have some absorbance. So I will just put few points. So let's say this is for 0. Then for when I increase the concentration to 10, my absorbance came somewhere like here. Then again with another increased concentration, my absorbance came somewhere here. Then again the fourth value, it came to be here. Now you can see that these are not lying in a same these are not lying on the same line. So if I try to put a point and connect these two, like you can see that they are not on the same line. So in order to get a generalized equation on a calibration curve, so that we can then later on determine the concentration of an unknown sample, we uh, generate an equation of this line, and the accuracy of that this equation, it is determined by the R square value. So these R square values, so the higher the value, the better is the accuracy. So among all these, 0.99, that is option C, it is having the highest R square value. So that is why it is having the highest accuracy. So for example, my this line, let's say it is having 0.99 R square value, and I have already plotted a calibration curve, and now I have given you an unknown sample. You don't know what is the amount of glucose in that sample. So what you will do is that you will put that sample in a cuvette, is a material where we pour a sample, and then you put it into the instrument. So your instrument is bound to give you some absorbance. Let's say the absorbance you got is somewhere here. If not here, let's yeah. So the absorbance you got, this is the absorbance, this value on y-axis. So now you want to know what is the concentration of it. So based on this curve, calibration curve that we have generated from the known samples, if you just draw this line down from here, you will get which concentration it corresponds to on x-axis. So that is why we prepare this calibration curves not only for UV spectrophotometer, for various other analysis and equipments as well. And while preparing this calibration curve, the accuracy of that curve, it is determined based on the R square value. So now moving on to the next question.
Can you please just clarify again what is R square value? I kind of lost it.
Okay, so R square value is basically, it is an statistical parameter which determines how much accurate your equation is. For example, you can understand, like, I had these known concentrations corresponding to which, let's say, these were the absorbances which I got, the readings which I got from an instrument. Fine. So I will plot this on an xy axis to generate a straight line of a constant slope, so that later on, if I am getting any unknown sample, I will just put it there, get its reading of absorbance, and then correlate its corresponding concentration. So first things first is that we need to first generate this straight line with a constant slope, and this is called calibration curve. So while generating this curve, it is not always like, if these values, you can see that these are the data points. Let's say my calibration, one data point has gone here, and this is another data point, it has gone here. So if this is the line generated, you can see that it is not that accurate because it is very much distant from these two other readings. So its R square value is bound to be, R square value is kind of gives you the accuracy of this equation that you have determined. So its R square value is bound to be very less. Let's say it is 0.7 or 0.6 or 0.6, let's say. Now, for example, you have again repeated this experiments. At that stage, the data points, it came close to this line for both of these. So you can see that now your calibration curve, that is this straight line, it is appearing to be much more accurate because these data points, it is coming very close to the line that you have assumed to be a calibration curve based on which you are going to determine the concentration of an unknown sample. So whenever these data points, they are coming close to that calibration curve, it means that your accuracy of this calibration curve that you have first plotted, it is improving. And when it improves, you can determine it by seeing a subsequent increase in the R square value. So its R square value is also increased like this.
Got it. And this known samples on which the absorbance has been identified, that could be anything.
Yeah, like I just gave you an example of this spectrophotometer. For example, you are using some another instrument like let's say ICP. There was one question on ICP that you are going to have that. So in ICP, what we do is that we determine the concentration of elements that can be heavy metals, these kind of stuff. So let's say you have a liquid sample. In that you have certain amount of you can say mercury, and you don't know it. So first things first, you need to train your instrument how to read the levels of mercury. Like that instrument, whenever you procure an instrument, and high-end instrument that costs more than 1 crore, 2 crore, that instrument itself, it doesn't know what like it doesn't know how to read the concentration of mercury or something. So what is done is that you prepare some known concentration of your samples. Now, if some instrument is reading that sample in terms of absorbance, the results will be in those respect, in those units. And if something is reading in some other values, it can be that also. So when I'm talking with respect to ICP, then you prepare known concentrations of mercury, and for those known samples, you get the readings from the instrument, and then you plot such a calibration curve. So this curve set defines, like based on the known concentrations, what my general equation is, so that if I am getting a sample which is having an unknown concentration of mercury, I can determine it by just correlating it back to the this absorbance can be any other instrumental value, and by like back tracing it, I can determine the concentration. So
Okay.
it's like that.
So it's unknown concentration, not the unknown compound that we will
Yeah,
know.
this is for unknown concentration. For unknown compounds, we do, for example, you might have heard about chromatography. So gas chromatography coupled with mass spectrophotometry, like this is one technique. In gas chromatography, what happens is that you get, like chromatography is basically, as we have read in our classes, in a chromatographic column, different chemicals, they get separated at different stages. So in gas chromatography, what happens is that there is an X and Y axis similar to this. I'll just copy it. Fine. So I have copied it. And then in gas chromatography, when you run that instrument, you get certain peaks like this at different time intervals. So in x-axis, you have the time, and in y-axis, there's an intensity. So these peaks, they correspond to different chemicals, and you don't know what chemical it is. So for those instances, you use mass spectrophotometry. So this mass spectrophotometry, it determines the unknown, like it tells you which is the unknown sample present there. But you won't have any idea, like the mass spectrophotometry will only tell you or identify this particular compound. For example, if this is glucose, it will tell you that glucose, for a certain combination of materials, glucose shows a peak. If this is 2 seconds, this on x-axis, glucose shows a peak at around 2 seconds. Let's say this is 2 seconds, this x-axis. The mass spectrophotometry will give you that, but you don't know what the concentration of glucose is. So what happens is that you will prepare different concentrations of glucose sample, and if you want to prepare a calibration curve based on gas chromatography, so you have to look under the area under this curve. That is, you can see that this all this part, for example, you can just, so the area under this peak, this basically gives you the, it can spread out a bit like till here, like this, till the base of this line, till here you will get the area under this curve, till here, let's say. So for a certain glucose concentration, this area will be something. If you increase the glucose concentration, this area will also increase. So you are, the instrument is calculating the increase in area along with an increase in concentration. Like this is what you are doing, like same thing in here. Concentration is here, and in here instead of absorbance it will be area under curve. So let's say it is also increasing with as I increase the glucose concentration, this area will also keep on increasing. Then in a certain unknown sample, you get an area something like this. You get an area something like this. This is a bigger area. So based on that, on unitary method, it will just correlate it to the concentration that is corresponding to this area. Am I clear?
Yeah.
Okay, so this is the difference. Fine. So moving on to the next question. Okay, so EPA is Environmental Protection Agency in US. It is a fill in the blanks. It recommends a minimum of okay. So what is the minimum number of samples that you must uh, analyze to get a significant detection limit value? Your options are 7, 10, 6, sorry, 6 and 8. What is the minimum number of stamp samples? So this is kind of a more memory based question. You have to just know them based on different guidelines. So based on EPS guideline, it should be minimum 8. There should be minimum 8 such readings taken. And a method detection limit, which is also known as MDL, it is basically used to, like, you get different equipments which are meant, for example, you have got an equipment from which you want to know the concentration of glucose in different liquid samples. And for that, you have got different instruments. You have got GC, you have got spectrophotometer. In fact, if even if you have get like if you have the same instrument GC, different kinds of GC may have different detection limits, and detection limit means the minimum concentration of the sample that that instrument can tell you that it can detect. So it depends or it varies from one instrument to another, from one method to another. But in order to determine what is the method detection limit, the minimum number of samples that you need to analyze, it is 8. Fine. So the next question, it is a numerical based one. M says moisture content. So you have to find the concentration of iron on dry weight basis in a sludge whose concentration has been provided to you with respect to the overall total weight, which is 3 milligram per liter, and you have been also provided with the moisture content of that sludge. So now you have to determine the concentration of iron on dry weight basis, and your options are, all the options are in milligram per kg only. So 60, 45 and 40. Please let me know in the chat box so you can unmute yourself when you have calculated this question. Okay, fine. So I will. Okay, so I will share the solution. Fine. So you have, like, if you want to look at it simply, you have 3 milligrams of what is it, iron in, let's say, 1 kg of sludge. Fine. So, and your 1 kg of sludge, it is having 95% moisture content. So, if I look at it from that perspective, so my 1 kg of sludge, or my 1 kg sludge, it is equal to 0.95 kg of water plus your 0.05 kg of whatever is the dried sludge, like the actual solids, if I must say. Rest, it is all water. Fine. So this is what is there in 1 kg of sludge. And you have been asked to determine the concentration of iron on dry weight basis. And dry weight basis means remove the water and then calculate it. So if I want to look at this particular scenario from a dry weight basis, it will be my 3 milligram, like iron will remain the same, but the amount of sludge it is in, it will differ. My 3 milligram iron is practically, if I am trying to look at it from dried perspective, then 1 kg of sludge is having 0.95 kg of water and just 0.05 kg of dried sludge. So from that perspective, 1 kg of sludge, it will transform into just 0.05 kg of dried sludge. Fine. And now if I want to transform it into this milligram per kg, it will become 3 divided by 0.05. How much it is? 60, I guess. Is it so? Yeah, 60 is the correct answer. Am I clear, or do you want me to explain it again?
Got it.
Okay. So moving on to the next question. Okay, so this is a theory-based question. Chem means chemical, CNC means concentration, chemical concentration in colorless liquid. I hope the question is clear. For finding the chemical concentration in colorless liquid, the dash of dash light, first you have to say the which property you are trying to determine, that is the first fill in the blanks, of which type of light. Is it a visible or is it a UV light? In 1 centimeter cell is measured in spectrophotometer. So first option is you need to identify what characteristic you are trying to measure, and second fill in the blank is with which type of light or with which wavelength. This is I just explained this while we were discussing this absorbance based R square value on similar concept. Any thoughts on this? Spectrophotometer, we were just discussing this. And this 1 centimeter cell, where we pour our liquid sample, this cell is called cuvette. Any answer, like which is the property that I am trying to determine and what will be the type of light that will be thrown on that sample or irradiated, being a much more technical term? Option A. Don't know whether this was for the previous question or this one. So like we were discussing in the other question, this is basically related to a UV spectrophotometer. So in a UV spectrophotometer, it basically determines the concentration of different materials based on the absorbance of that particular compound or element. So first thing is first, absorbance is what I am looking for, and second part, by irradiating it with a UV light. So initially, if there is something colorless, then the UV spectrophotometer, it is basically pointless. So it should have some color. So that is why we, during analyzing it, we add certain chemicals, and while adding them, a certain amount of color is generated, which color is then related to the concentration of a material. So then we determine that by correlating these two aspects, we then determine the concentration. And the cell in which it is being poured, it is called cuvette. Cuvette is basically, you can say how to draw this. It is basically a cuboidal kind of material. Okay, 3ds. Okay, so this is kind of a cube, but the thing is, I'll just try to draw it here. So it is a rectangular top projection and then a cuboidal kind of cell wherein we pour our samples. So let's say this is one side of the cell. Okay, I can use this. So you can see here that this is a mobile charger basically, but you can think of it as a 1 centimeter cell. Each dimension, it is a cube dimension, the top one is square, and each dimension is 1 centimeter length and breadth, and then it is projected to like this much long, it is 5 centimeters, something like that, and we pour our samples there. Okay, so it has got how many faces does a cube has? So it has got 1, 2, 3, 4. On this perspective, I'm not taking the top face and bottom face, so it has got 4 faces. So what happens is that I insert my sample or this cell, or which is technically called as cuvette. I insert my cuvette into the apparatus. So what happens is that these two faces, these are translucent. That is, the light can't properly pass through these two uh, sides of my cuvette. So that is, and why is it done so? So that I can hold my cuvette like this. And these two sides, this one and this one, these are completely transparent. So what happens is that I put it like this into my spectrophotometer, and then the UV radiation from this side, you can see from here the UV radiation, it hits the cuvette and then it passes through it, and the absorbance is determined. So this part and the opposite one, this part, these are completely transparent, so that there is no disturbance for the UV light to pass through the sample. On the other hand, these two parts, these are translucent, and the reason behind this is that so that I can hold it from these two sides. Because if I am holding my sample like this and my fingers are touching on this transparent part, what happens is that when I remove my finger and I just put it inside the instrument, my fingerprint, something like it will be present here. And those minute fingerprints, in fact, they can give a completely wrong result. So that is why we never hold the sample or the cuvette like this. Sorry, like this. On the transparent part, we never touch it on the transparent part, so that there is no smudges, no fingerprint, no stains on this transparent part of the cuvette. Always we hold it from the translucent part, because anyways my light is not entering through these translucent parts. They are not taking part in this process. Only this transparent part is taking place. So that is why keep these parts completely clean so that the light can pass through it efficiently. Put it inside the sample. In fact, what happens is that when we pour a liquid sample inside the cuvette, like it is similar to when you are pouring some water inside the bottle, you will see that there is some tiny bubbles present there also. So we should also be very careful that no such bubble should be there inside this cuvette or this cell that we are talking about. Because if there is any bubble present inside it, it will also seriously affect the absorbance, because then the path length through which the UV radiation is passing through, it will be different, because in this bubble part there will be no chemical in that part, there will be no liquid in that part, because that is basically air. Rest it will pass through the liquid sample. But since it is also passing through that bubble will lead to an error in the total results, the final result that you are having. So that is why when you are pouring the sample, be very careful that there are no bubbles present inside the cell. If something bubble is left behind, we just uh, like hit our sample lightly like this, the cuvette, so that those bubbles are coming to the top and then passing out. So this is how we use spectrophotometer, and the cuvette is how it is handled. I hope that is clear. If you have anything you might want to share, or you have any doubts on this, please feel free to unmute yourselves and speak out. Fine. So moving on to the next question, which will be question number 11. Okay, so according to the solid waste management rules, no person shall organize an event or gathering of more than dash number of persons at any unlicensed place. Your options are 90, 100, 80, and 50. Just 10 seconds to think about this. Okay, fine. So this value should be 100. No person shall be allowed to organize or shall organize an event or gathering of more than 100 number of persons at any unlicensed place. If you want to organize any event for where you are expecting more than 100 people, then you have to first intimate the relevant authorities at least 3 days prior to the incident or this event, 3 working days. So there should not be Saturday, Sunday, or such holidays in between. At least prior to 3 working days, you should inform to the authorities that you are planning such events. Now, next is a numerical type of question where it may take some time for you to calculate. It is an easy question, but a bit lengthy. Chromium concentration, Cr. These are the concentrations, and you have to determine the mean value. Very easy. Your options are 3.25. Sorry, this question is actually a very simple and short one. The other question is, I think that is a lengthy one. That is also easy. Fine, so short questions. And like you might be expecting like why the necessary or why it is necessary to do such a number of repetitions of a sample, because I'm trying to determine the chromium concentration, and you can see that in all those values it is somewhere 31 point something only, not 32, not 33. But this concentration, when I'm talking about these kind of toxic and hazardous heavy metals, it is very important to be very precise, because based on that only we will design different other treatment methods. And in fact, when we are doing laboratory experiments for different purposes also, we repeat a same experiment with same condition at least 3 times. Why this is done? It is very obvious. It is done so that we can see how much is the deviation in the results that we are seeing. Now, in lab scale, when we are performing experiments, it is not possible for us to go for this many number of readings or this many number of runs we can't do, because each experiments it might take different time. We have to go through the analysis. So for that, traditionally, and it is a practice that we should do at least 3 runs so that we can get the average and standard deviation values of different kinds of experiments we are doing, and that shows how much reliable or how much variance is there in the data or the results that we are getting. And for doing waste characterization also, for example, you are an engineer and you have been asked to determine the concentration of, let's say, microplastics in river Ganga, if microplastics or any other pollutant in river Ganga at different points. So for that, there are specific formulas where first, which let you know how many number of samples you need to collect and at what places. And those numbers, it can go up to very high, as easily more than 50. Because when you're doing such a characterization of a environmental pollution at different places, different environmental matrices like river or soil or somewhere, you need to collect a huge number of samples, for which there is a separate formula which tells you how many number of samples you should do, and based on that only you can get a total picture, like what is the concentration of different contaminants at different places. So I hope you must have got the answer for this. It is very easy, and I will just tell you the right answer is option C, that is 31.23 ppm. Now the next question is based on method detection limit. What is the MDL, that is the method detection limit, with a 99% confidence level for the sample analysis results? Just let me cross check the values. Okay. And the data are same. And these are the concentrations that you have been given. And your options are, these are the options. What is the method detection limit? Okay, sorry, these are the wrong options for the previous question. And for this, I will also give the formula that we use. MDL is equal to T is the T value for n minus 1, comma, okay, so this is the formula. T value, you have to calculate it based on n minus 1, and alpha is the confidence level, which is 99% given alpha, and n is the number of samples, which you can see is 1, 2, 3, 4, 5, 6, 7, 8. 8 samples, so n minus 1 is 7. And for this T 7, 0.99, the T value will be, I am also giving you this. Although there is a T table for it, which you can anyways refer to later on. But for now, this is the T value that you will get for T in bracket 7, and S is the standard deviation. So this is what you need to calculate for this question. Since this might take some time to calculate the standard deviation, you can have 10 minutes to go through this and let me know if you are having any problem with it. Okay, so if you can calculate the standard deviation with a calculator, it will must be pretty easy to calculate that. So I am giving you the standard deviation result that I have here. The value of standard deviation, yes. So that should be 0.20. So based on that, we can calculate the MDL, which will be 0.20 into 3 ppm. So this is the method detection limit of a certain instrument or a technique that this question was discussing about, 0.6 ppm. Now the next question, it is, yeah, a theoretical based question. Standard deviation, how to calculate? Like it is very easy. First you have to calculate the averages. Like what is the average of this? You have calculated in the previous question already. Now for each sample, for each result, you have to like see how much that 31.21 is deviating from that whatever your average is, and that is the standard deviation for individual samples. Then you have to calculate the overall standard deviation. So this is a pretty easy thing to calculate the standard deviation. You can go through Google. I think you will can quickly learn how to do calculate the standard deviation. In fact, if you have a gate calculator or any other scientific calculator, it can be done there as well pretty quickly. So standard deviation is basically deviation from the average value. Then for individual values, you need to calculate it, and then the overall one. Now the next question is, which instrument is used for analyzing the heavy metal concentrations in the sample? I will just give you the options. Again, I am repeating the question. Which instrument is used for analyzing heavy metal concentrations in samples? The samples can be both liquid as well as solid. Option A. Okay, so which one do you think of these four instruments will be used for calculating the concentration or like analyzing the concentration of heavy metals? Any idea? Just like in one of these examples, I have already talked about these things. You can use the chat box as well if you have. Okay, so ICP, option B is absolutely correct. ICP is the correct answer. That is inductively coupled plasma. It is used to analyze the concentration of heavy metals. And the other ones, gas chromatography, liquid chromatography, and other things, they are basically meant for organic compounds to identify them. First, gas chromatography alone cannot be sufficient to identify your, for example, you have wastewater in which there are various dissolved organic materials. Just doing gas chromatography will give you certain peaks like this, but these peaks will be present at, let's say, at 2 seconds, then 3 seconds, 4 seconds. That means at 2 seconds one material or compound has has been separated, then in 3 seconds something else, and 4 seconds something else. This will give you just the peak locations, but you won't be able to identify the unknown compounds. For that, you do mass spectrophotometry, from wherein, based on the molecular weight and the intensity of the signal, you determine like what the unknown compounds or materials or molecules can be. So that is what gas chromatography do. Similar is the concept for liquid chromatography as well. Mass spectrophotometry again is used for identifying the known organic compounds. High performance liquid chromatography is an upgrade to the liquid chromatography. Same concept, but basically a more upgraded and refined technique. And among these, inductively coupled plasma is used for heavy metal analysis. Now in this, what happens is that if you have a solid sample, first you need to know the concentration of any heavy metal which is present in, let's say, 1 gram of solid sample. So what happens is that first you need to digest that sample, and by digestion what I mean, you need to convert it into a liquid sample. So what is done is that you add very concentrated nitric acid. There is a certain protocol for that as well. So you add concentrated nitric acid, it dissolves all the solid particles, it dissolves into the acid, and then it has been converted into a liquid sample. Then that liquid sample is further injected into the instrument, which further like converts it into an aerosol kind of material. That aerosol kind of material, it then goes into a region where plasma is generated. That plasma is very highly superheated region, and in that plasma what happens, since it is heat, it is a form of energy. So that energy is like transmitted, not transmitted, that energy is what can be the correct term, like it is incident on the atoms, the heavy metal atom. Now that atom has got an electron cloud around itself. So that electron cloud first absorbs the energy. Once it absorbs the energy, it becomes excited. So that is not the stable state of any material. Once it absorbs the energy and it gets excited. So what it does is that after quickly after some time, it again emits that energy back at a certain wavelength and comes to its stable state. Now the emitted wavelength of energy that a certain metal emits, it is kind of a signature wavelength. Chromium and mercury, both of them will emit different wavelengths, and my detector which is present in the instrument, based on those wavelengths, it identifies like which is the material present in there. And for example, if you are getting huge intensity of this mercury's signature wavelength, then that means that more is the concentration of mercury in that sample. Similar for chromium or anything else. So first things first, if you have a liquid sample, it is fine, you can directly inject it into the equipment. If you have a solid sample, you digest it using strong acids. That digested sample is inserted into an instrument. The instrument then converts it into tiny droplets. Further, those droplets are converted into aerosol kind of form. Those aerosols then reach a plasma region, superheated region, where the atoms of different metals, heavy metals, they absorb the energy. Once they absorb the energy, they become super excited. Then quickly they also come to this back to their stable state by releasing energy. And that energy that is released, or that wavelength of energy or emissions that is released from those atoms, it is like a signature emissions for different kinds of metals present there. So based on those signature emissions, the detector identifies which element is present, and on the intensity of those emissions, the concentration or the amount of that it is present in a certain mass, it is determined. So that is how basically an inductively coupled plasma works, or ICP. So now we have the final question, question number 15, which is a true and false type of question. SWM 2016 means Solid Waste Management 2016 rules. So resident welfare and market associations, gated communities and institutions with more than 5,000 square meter of area, hotels and restaurants in partnership with local body should ensure waste segregation at source as prescribed in SWM rules. Whether this is true and false, it is a very obvious question, and I think you will be just right away guess the answer. Yes, it is true. That is the correct answer. Now, few points on that. Okay, so like whenever the waste is segregated based on this area, the amount of people living there, you can segregate it, and that after that, the amount of waste that is present there. For that, there are guidelines which say whether you should compost it. Also, the characteristic of that waste also defines the management policies on management approach as well. For example, if there is a organic fraction, how much moisture content it has, what kind of material it has, so that also defines it. And generally speaking, the based on the amount or the size of that area, if you have got an organic fraction, it will define whether you should go for methanation or composting. And if you are going for composting, composting can be done at a small scale bins, like you can develop a bin in your households, do composting there, or you can have a huge area allocated for this composting. Windrow systems are there where you can mechanically mix those compost from time to time, the feedstock, and then manage your wastes. So this all depends upon the area and as well as the population of that place. So these were the 15 questions that we had for us today. If you have anything else that you would like to discuss, then you are free to unmute yourselves and share that with us. Otherwise, we can meet again in the next week, that is a week 4 live session on the coming Monday again from 7 to 9 p.m. Okay, what is lignin? So basically, if I'm talking about in terms of biochemical composition of any waste, I am talking the example of a tree. If I'm having a trunk or any leaf as well, it has got three major components: lignin, cellulose, and hemicellulose. Lignin is kind of an aromatic kind of structure, and it is, if I compare it or if I try to talk to about it in terms of biodegradability, then a microbe is there, and if I am trying to see whether and how efficiently it can degrade lignin, hemicellulose, and cellulose. Cellulose is most easy to degrade, followed by hemicellulose and then lignin, primarily because the degree of aromaticity, that is the aromatic structures in lignin, it is much more than in cellulose and hemicellulose. So in biochemical composition, lignin is the amount of a certain chemical that is present in a material. And lignin is always found in various leafy vegetables, trees, and all those materials. Am I clear, Mohammad Hashim, or anything else? Okay. And also, like when we are composting or biodegradability of a stuff that we are of a waste that we are checking, then it is very important for us to determine the lignin content in it. For example, newspaper. Newspaper, it is prepared from paper, coming from those trunk material as well. It is processed and all. So newspapers, they have got a like very high lignin content because cellulose hemicellulose is very insignificantly like significantly less. So for example, if you are having any waste which is like, if you can say, it is organic in nature, but the lignin content is very high, it is having very high lignin content, then that would mean that it would be very difficult to biodegrade it. It can be biodegradable, but the time taken will be much higher because it is difficult for the microbes, the bacteria, to break those aromatic bonds and then degrade those materials. Hydrolysis and all those hydrolysis, acetogenesis, these things will take time when you are trying to degrade a waste which has got huge lignin content. So for that, if you have got such a waste which has got huge lignin content, many people, what they do is that they first pre-treat the waste. And one of the most frequently used pre-treatment methods can be like one is enzymatic hydrolysis, then thermal hydrolysis, then acid hydrolysis or base hydrolysis. Then what it basically means is that in all these processes, we first put some strong agents. It can be heat in terms of thermal hydrolysis or acid or base or enzymes, which first break certain amount of bonds in that lignin. So once some degree of bonds have been broken externally before it is subjected to bacterial degradation, then the bacteria which is then going to get that pre-treated waste, they will find it a bit easier to further process it than the original lignin rich waste that initially was there. So that is why such lignin rich wastes are often pre-treated to make it more easier for the microbes to work on them. Anything else? Okay, so if there are no more questions, like I would like to again highlight. Okay, I will just quickly go through the questions again because some of the attendees who are present in this meeting, they might have joined late. So quickly going through all the questions. First question, combustion of the waste composition can be considered for characterizing the combustion potential of a waste. So basically, which type of composition should we look at when I am trying to look at the combustion characteristics of a solid waste? So the correct answer was fixed carbon, volatile solids, inorganic, ash and water. Next question was calculating the heating value of EDTA whose chemical formula was given. So you can calculate it based on this BTU per pound, and this is the formula which is known as Dulong's equation, where C, H, S and N as well as O, these are all, you have to fill the values in percentages, like percentage of C, percentage of H, O and S and N. Here it was done, those calculations. Then preferred measurement unit for chemicals present in solution, very obvious, we'd measure it in milligram per liter or ppm. Then if a BOD of a sample is 0.05%, what will be its BOD in terms of in the unit milligram per liter? So 1% is equivalent to 10,000 ppm. Based on it, you can correlate to 0.05% what it will be. Followed by waste generators should segregate their waste into two streams, biodegradable and domestic hazardous waste, according to SWM rules 2016. Whether it is true and false? The answer is false, because it should not be segregated into two. It should be done in three sections. One is the biodegradable, non-biodegradable, and third one is the hazardous waste. Biodegradable, non-biodegradable, we all know plastics and all those stuff. Biodegradable means your food waste, vegetable leftovers, those materials. Hazardous waste will often include the batteries that you use in your homes. That can be inverter batteries, UPS, or any electronic hazardous waste, or the batteries, that small cell batteries, what you call them, coil cell batteries. Those materials, they contain hazardous waste because these batteries are having electrolytes in them, which are really corrosive, and they can degrade or reduce the efficiency of the waste management process through which the municipal solid waste will go through if these hazardous components are not removed prior to it reaches those locations. Then again was next question was 4 calibration graphs were provided, and you have to choose one which has got an acceptable R-square value. So basically, higher the R-square value, the better the acceptance of a graph is. And now what is R-square value, from where this concept is coming? The calibration graphs are basically graphs which are first plotted using known concentration of different molecules or compounds for which we are interested in an unknown sample. For example, you want to determine the concentration of glucose in a, let's say, wastewater. Then what will you first do is that you are using any instrument, let it be UV spectrophotometer or gas chromatography. First, you will prepare 4-5 known concentration of glucose samples. One of them will be blank. Then you will put it into the instrument and see what is the reading that the instrument is showing. So your x-axis is the known concentration and y-axis is the instrument reading. You will plot a graph like this. These dots are the points which you are getting for different concentrations. Then what happens is that after that you generate an equation of a straight line constant slope which provides you the which is called known as the calibration curve, and that curve is used to determine the concentration of an unknown sample. And how accurate your curve is, that is determined based on the R square value. So the higher the R square value, the better it is. In terms of practical field application, the R square value should preferably be always greater than 0.95. So if you can see here, if these are the data points, and the line that you can see here, the slanting line, this is the equation that we have generated. Okay, let's say my data point is somewhere like this, and this is the line that was generated. So you can it is very much evident that this line, it is not very accurate, because few of my data points are so much far away from this line. So such lines will, or such equations will have an R square value very less. It can be 0.5, 0.3, or lower than that. Once these data points, they start coming closer to this line or falls on this line, that indicates that the equation which we have generated, which we call calibration curve, it is much more accurate because it is giving very close results to the actual reading that I am getting from the instrument. In those instances, the R square value increases and it's somewhere preferably more than 0.95. So that is the R square related question. Then EPA, that is the Environmental Protection Agency in US, it recommends a minimum of 8 number of samples to be used to get a significant method detection limit value. Method detection limit is the minimum detection limit of a different methods, processing methods or equipments. Then next question was, your iron concentration in sludge was given as 3 milligram per kg. It was a wet sludge as it is generated. So the sludge had a moisture content of 95%. You had to determine the iron concentration on dry weight basis. So it was calculated like this: 3 milligram of iron was present in 1 kg of sludge, and this 1 kg of sludge basically constitutes of 95%, that is 0.95 kg water, and 0.05 kg of dried sludge, that is the solid particles. So if you want to determine the this iron concentration on dry weight basis, what you will do is that this 3 milligram of iron is present in basically in 0.05 kg of dried sludge. Just divide 3 by 0.05 and you will get the answer in 60 milligram per kg of dried sludge. The next question was for finding the chemical concentration in colorless liquid. The first dash is absorbance of UV light. Next, fill in the blank is UV light. In 1 centimeter cell, this 1 centimeter cell is known as cuvette, is measured using spectrophotometer. The next question was regarding SWM rules of 2016. No person shall organize an event or gathering of more than 100 number of persons at any unlicensed place. In case if you are organizing an event in an unlicensed place and you are expecting more than 100 people to gather there, you need to inform the relevant authorities at least prior to 3 working days. So there should be a gap of at least 3 working days from your event when you have to inform the authorities about that. The next was very simple. You have given various readings in ppm. You have to determine the mean concentration of chromium. Very simple. Followed by method detection limit, a very important question, in which 99% confidence interval has been provided. Same data for the concentration of chromium. And how to calculate MDL? The formula is this: T value is determined based on T. You have to find n minus 1 comma alpha, which is already the confidence interval, confidence level, which has been provided 99%. So that is in fraction 0.99, and n minus 1, n is the number of samples. We have total 8 readings here, or 8 samples, so n minus 1 is 7. So T value, you can get this from the T table, for 7 comma 0.99 is 3. Standard deviation you have to calculate for these readings, which comes out to be 0.2, and then method detection limit is T value multiplied by standard deviation, which is 0.6 ppm. Now next question was, different instruments were provided to you. These were the instruments, and you had to choose which one is suitable for calculating or analyzing the presence of heavy metals. So the correct answer was electrically coupled plasma. After that, the final question, I guess, yes, it was the true and false one. Resident welfare and market associations, gated communities and institutions with more than 5,000 square meter of area, hotels and restaurants in partnership with the local bodies should ensure waste segregation at source as prescribed in SWM 2016 rules. So this is true. So these were the questions that we had in store for us today. And The time is also up, so we will be meeting again in the next live session in the coming Monday from 7 to 9. So thank you all for being here today. Looking forward to see you again. Take care. Goodbye.
Sir,
Yes.
sir, when we mix two waste streams,
Yeah.
how can we find the density of it, sir?
So density is very simple. So when I am mixing two waste streams, first you have obviously got the volume, and then you can also have the density by this water displacement method if that thing is solid based. But if you're mixing two waste streams, and you need to know the density of individual waste stream.
They are
So one
known, sir.
so
Suppose
indi
they are known.
oh if
Individual
the,
wastes are known.
okay, so then it is simple. I will just share my screen again. Okay, just give me a moment. Okay, so you have two waste streams whose individual densities you know, and you are mixing them and you want to know the overall density, right?
Yes, sir. Right.
I hope my screen is visible. So let's say this is S1 stream 1 and this is stream 2. Here the density is, let's say, 2 kg per meter cube, and in here it is 3 kg per meter cube. And now you have to determine, like, you, let's say the scenario is you are mixing 1 kg of S1 with 2 kgs of S2. So total you have 3 kg and you want to get its overall density. So in here we calculate it like this. So for S1 I will write M1 is equal to 1 kg, and for this let's say M2 is equal to 3 kgs. Fine. So overall volume 2 individually we calculate. What is the volume of this? It will be 3 divided by 2. Similarly for this also, V1, it will be what? 1 divided by 3 meter cube. So individual volumes of these two wastes that we know. And now after that it will be very simple. The total mass is equal to 1 kg plus 3 kgs, which will become 4 kg, and the total volume will be 1 by 3 plus 3 by 2. So after that you can calculate the total volume. 1 by 3 is 0.33 plus 1.5 is equal to 1.83. So this is the total volume of the waste, mixed waste, and this is the total mass of the mixed waste. So just divide mass by volume, and that is how we calculate the overall density of the mixed waste. Is it clear?
Sir, should we do the average of both of these?
No, average, like average of what? Density?
Yes, sir.
No, average of density we shouldn't do there. Basically, what we are trying to do is that it is, you can say, weighted average, because what happens, you could have done the average of these two if you would have had 1 kg of waste 1 and 1 kg of waste 2. But if you are, these two masses are different, of two different waste streams, then the average will not work. Then what we do is weighted average. So weighted average are basically this thing. This is a more simple way to visualize.
Okay, sir. Thank you, sir.
Okay. Okay, then see you again next time. Take care. Bye.